why at the end of chapter 3, when we introduced how to write sentences in the language of chemistry, we say you must balance your equation to begin with. Okay? So when you balance the equation there, what it means here is that you have the number of atoms on the reactant side that equals to the number of the same atoms on the product side there. So that's what we mean by a balanced chemical reaction equation. Quick a review of what we talked about at the end of chapter 4, end of chapter 3 there. Okay, so in this particular, well, we actually did this as our last practice there. In this balanced chemical reaction equation, 2 moles of ethane will react with 7 moles of oxygen gas and generating 4 moles of carbon dioxide and 6 moles of water. Now, the question here is that when we try to quantify the chemical reaction, how many moles of water are produced if you have 3 moles of oxygen to react? Well, this is a new type of chemical calculation. Well, as I told you at the beginning, there is no new type of calculation, it's just dimensional analysis. All you need to do is, given this information, how do you identify the correct conversion factor? Once you identify the correct conversion factor, all you need to do is the quantity you need to convert, multiply by the conversion factor, make sure you focus on the unit. Unit cancels out, leaving you with the unit you do want. So in this case, let's see how we do a dimensional analysis in this particular question. Now we have 3 moles of oxygen. Okay, that's the reactant. We want to know how many moles of water can you produce. So if you have, this is how we're going to set up the equation. We want you to convert 3 moles of oxygen into X moles of water. Okay, so if you have 3 mole of oxygen, we want you to multiply the conversion factor. What is the conversion factor? Well, given the balanced chemical reaction equation, we know there is a relationship between the number of moles of oxygen and the number of moles of water. That is, for every 7 moles of oxygen, you can produce 6 moles of water. Now, if you multiply the moles of oxygen by this conversion factor, moles of oxygen cancels out. What's left? Wake up. What's left?
Oxygen.
Moles of water. Oxygen cancels out. What is the question asking you? How many moles of water can we produce? So, dimensional analysis. Nothing new here. What I need you to do is to figure out the conversion factor. This conversion factor is given in this balanced chemical reaction equation. That's what the calculation is all about. Now, if you do the calculation, 3 times 6 divided by 7, you end up with 2.6 moles. 2.6 moles of what? 2.6 moles of water. Okay, so that's the calculation. So if you have 3 moles of oxygen, you will be able to produce 2.6 moles of water. The calculation simply appears in a different format, but it's dimensional analysis. All you need to do is to identify the conversion factor. The conversion factor is given in here. So we will give you a list of equivalent quantities, and that's our conversion factor. We will give you a periodic table, that's our conversion factor. We will give you a balance. Well, sometimes we give you an unbalanced chemical reaction equation. You have to balance it. Once you balance the chemical reaction, that's our conversion factor. So all the information directly given or hidden in these different sources there, you have to be able to dig them out and then plug them into the calculation there. Once you identify the conversion factor, the calculation itself becomes very easy. It's just 3 times 6 divided by 7. Focus on the unit and the materials involved in here. So moles of oxygen cancels out. What's left? Moles of water. And what is the question asking you? Moles of water. So you can, based on this type of setup, you can clearly see you get the correct answer. The other side of the coin there, same reaction, we can ask you, now, if you must produce 1.75 mole of carbon dioxide, how many moles of ethane do you need? Well, that's another dimensional analysis. We are asking you to convert moles of carbon dioxide 2 moles of ethane based on the balanced chemical reaction equation. You set up the equation the same way, 1.75 mole of carbon dioxide. Conversion factor, we need to cancel out moles of carbon dioxide. So moles of carbon dioxide has to be on the bottom in the conversion factor there for this particular calculation. Okay, so we have 4 moles carbon dioxide. What's the relationship between carbon dioxide and ethane? Well, every 4 moles of carbon dioxide, based on the balance equation, requires 2 moles of ethane. If you do this calculation, if you do this dimensional analysis, carbon dioxide, moles of carbon dioxide cancels out. So 1.75 times 2 divided by 4, the number by 2. You end up with 0.87. How many sig fit? And that's always going to be a question. How many sig fit? Well, 1.75, that's the measured quantity, 3 sig fit. So the answer should have, this is 4 sig fit?
3.
Leading zeros are non-sig. This is something that you have to know. Okay, so 3 sig fit there. That's the number of moles of the ethane. So this is the number of moles of ethane required if you need to produce 1.75 mole of carbon dioxide. Once again, there's nothing new. All we are trying to set up here is that in this course, 95% of the time when we're doing a calculation, it's about dimensional analysis. All you need to do is to identify the correct conversion factor. Once you have the correct conversion factor identified, the rest of the calculation is easy. You just punch in the number in the calculator. Watch for the units and the chemicals involved in there. You have to be able to cancel out. When you set up the equation there, you have to be able to cancel out things you don't want, and you end up with the things you are asked for. You're being asked in the question here. So this is the calculation part, stoichiometry. Okay. It may appear to be a little bit more complicated than what we have done before, but the essence of the calculation is still the same, dimensional analysis. Now we have a balanced chemical reaction equation. The conversion factor that we need is hidden in there. You just need to dig it out, plug it in, and do the calculation. Okay, so that was a relatively easier part of the calculation in terms of the stoichiometry. Here's another example there. And according to the statistics from EPA and other agencies there, in 2010, the average daily use of gasoline in this country is about 1.2 times 10 to the 14th gram. Now you measure gasoline in gallons, and when you go to the gas pump there, and you put in so many gallons of gasoline in there, and that's a volume measurement there. Now here, the measurement is in grams. Now we ask you if we consume, the humankind, if we consume this much gasoline in this country alone. Now there are 200 other countries on this planet. They also use gasoline and fossil fuels to power their, as a power source for their daily life. So if we consume this much gasoline, and we assume that gasoline is octane, carbon 8, hydrogen 18, we want to figure out how many grams of carbon dioxide is produced. Now, this calculation, we are asking you the conversion